Fill in the missing pieces in the following proof that 1 plus 3 plus 5 plus all the way up to 2n minus 1 equals n squared for every integer n greater than or equal to 1. Proof. Let the property P of n be the equation 1 plus 3 plus 5 plus all the way up to 2n minus 1 equals n squared. Show that P of 1 is true. To establish P of 1, we must show that when 1 is substituted in place of n, the left-hand side equals the right-hand side. But when n equals 1, the left-hand side is the sum of all the odd integers from 1 to 2 times 1 minus 1, which is the sum of the odd integers from 1 to 1 and is just 1. The right-hand side is, well, this is what we get when we plug in n equals 1 into the right-hand side of our statement P of n, which would be 1 squared. So the right-hand side is 1 squared, since n is 1, which also equals 1. So P of 1 is true. Show that for every integer k greater than or equal to 1, if P of k is true, then P of k plus 1 is true. So this is what we want to show here. Let k be any integer with k greater than or equal to 1. We're going to suppose that P of k is true. That's the goal here. Notice how this is a commentary, so this is not necessarily written down in the proof, but it's constructive to understand the flow of the proof. So we're going to suppose P of k is true. This is the left-hand side of P of k, and keep in mind P of k is the same statement as P of n, but we just have to replace all of the n's with k's. So here 2n minus 1 is now 2k minus 1, and on the right-hand side, instead of n squared, it would be k squared. This is the inductive hypothesis. We must show that P of k plus 1 is true. That is, we must show that, now this is the statement P of k plus 1. We have to write down the left-hand side of P of k plus 1 and the right-hand side of P of k plus 1. So the left-hand side of P of k plus 1 is going to be 1 plus 3 plus 5 plus ... all the way up to, I'm going to write out the last two terms explicitly. So the second to last term is going to be the same as the last term from the previous statement P of k. So that's going to be 2k minus 1. But then the last term is going to be now 2 times k plus 1 minus 1. So that's the left-hand side. The right-hand side is going to be what I get when I plug in k plus 1 into n squared, which would just be k plus 1 squared. So that's the right-hand side. Now, it's not necessary to write the second to last term here, but I think it's helpful to understand how this sequence progresses from both the beginning and from the end. It gives two different frames of reference of how this sequence progresses. Okay, let's keep going. Now, the left-hand side of P of k plus 1 is, this is what we just wrote down earlier. And now the next step is to simplify this last term here, which can be simplified to just 2k plus 1. And then the author pulls out that last term. So this right here is actually the second to last term, and we have simply pulled out that last term, 2k plus 1. And so now here we have the left-hand side of P of k, and then plus this last term for P of k plus 1. So this is still the left-hand side of P of k plus 1. It's just reorganized so that the first k terms of this series is grouped together, and the k plus 1th term in the series is pulled out. So the next to last term is 2k minus 1 because the reason the previous term is 2k minus 1 is because each time we go to the left by one term in this series, we reduce the number by 2. If we go from 5 to 3, that's subtracting 2. If we go from 3 to 1, that's subtracting 2. And so the reason why the second to last term in this series is 2k minus 1 is because 2k plus 1 minus 2, if we take away 2 from that, we get 2k minus 1. Okay, the next line says, which equals k squared plus 2k plus 1. Notice here that the author replaced this entire series with just k squared. But why are those two equal to each other? So this is because of the inductive hypothesis, which I'll just write as capital I, capital H. Now remember, the inductive hypothesis is the statement P of k. And so the reason why I know 1 plus 3 plus 5 all the way to 2k minus 1 equals k squared is because we get to assume that P of k is true, which means that 1 plus 3 plus 5 all the way up to 2k minus 1 equals k squared is true. We get to assume that's true by the inductive hypothesis. The next step is to simplify this quadratic. Now, we can simplify this a little bit more, I think. We can rewrite this quadratic by dropping the parentheses. And then we can factor this quadratic as k plus 1 all squared by algebra, which is the right-hand side of p of k plus 1, as was to be shown. This is what we wanted to show. We wanted to show that the left-hand side, in fact, equals the right-hand side of p of k plus 1, which is what we got by algebra, by the inductive hypothesis, by a bunch of logical steps. We showed that the left-hand side of p of k plus 1 is, well, it's this thing, but it's also equal to that thing, which means the left-hand side of p of k plus 1 is in fact equal to the right-hand side of p of k plus 1, which means that p of k plus 1 is true. And the assumption that we made to show that p of k plus 1 is true is p of k. So that means that the truth of p of k implies the truth of p of k plus 1. So that's what we just showed here. And this is called the inductive step. And then from here, we can say, by mathematical induction, we could say that p of n is true for all integers n greater than or equal to 1. Thanks, everyone, and I'll see you in the next video.